pilot wave theory. So pilot wave theory is an interpretation of quantum mechanics. So first we have to say, why is quantum mechanics important and what is it used for? So quantum mechanics is basically the physics of things on the quantum scale where classical mechanics fails. And so anything about the size of an atom or smaller, your normal classical equation mechanics or equations basically aren't going to work, and it's not going to be the same. So we use quantum mechanics for advanced transistors, semiconductors, lasers, photonics, quantum computing, sensors, and imaging. And that's the main reason we want to basically understand it more. So what is pilot wave theory? It's a relativistic interpretation of quantum mechanics, referred to as Bohmian mechanics. So what that means is that basically everything everything in pilot wave theory is deterministic according to this theory. So if you know the place where it is and everything about it, you can tell where it's going to be, and it's not just probabilistic. We can actually determine that. For the history behind it, it was first thought up by Louis de Broglie, and he was talked out of it actually by the main, those really famous scientists of that era. If you've seen that picture of all the scientists lined up, Louis de Broglie was in that picture, and he was actually talked out of it to basically believe in the Copenhagen interpretation, which is a counter-argument to the pilot wave theory. And it was later picked up by David Bohm, who took the Schrödinger equation and actually derived a guiding equation for pilot wave theory. So why pilot wave theory? It's a more deterministic version of the Copenhagen interpretation. So the Copenhagen interpretation says that a particle, or when you measure something, it'll be a particle, but it's always going to be a wave when not measured. So on the quantum scale, it's going to be a wave, but when you measure it, at the exact moment you measure it, it's going to be a particle. And what pilot wave theory says is it's the exact opposite, in which it's always a particle that is influenced by a guiding wave function. So it's a particle and a wave, and not either or, which is paradoxical. So it's basically taking that paradox and saying that this is an interpretation that we can actually comprehend, and that's deterministic. So here's the Schrödinger equation. Many of you probably know this equation, have seen it if you've taken quantum mechanics. We can actually derive this guiding equation from this. I'm about to go into how that's done. This is our quantum Hamiltonian Jacobi equation, and this is our quantum potential. We have potentials used in classical mechanics, but when you get to the quantum scale, you have to also include this quantum potential Q. So here's the time-dependent Schrödinger equation. I drew this out on a board real quick. Try to give an overview. It doesn't cover everything, but here's the main equation. Here's the expanded Hamiltonian H right here. This is the polar form of our wave function, and so you can express that in terms of R, amplitude, and S, our phase of the wave. And so we can write it out and we can plug it into the whole equation right here. And we get our time derivatives over here and our spatial derivatives right here. And then from this fully expanded out time-dependent Schrödinger equation, we can get imaginary parts and real parts. And then from this real part, it shows the evolution of the probability density, and the imaginary part shows the evolution of the S phase. And then from this real part, that's actually where the guiding equation is taken from. And it's influenced by quantum potential as Q, which in the previous slide down here. So the double slit experiment is the main so when we look at quantum mechanics, we're trying to determine how to interpret it, how to understand it, how to comprehend it. We're trying to figure out why this double slit experiment is happening the way it is. And basically what's happening is if you have a slit and you have something that's firing a photon or particle through it, classical mechanics says that its probability is going to land in this area, so we draw a probability wave. It's going like this, because it's shooting straight through, like shooting a gun at a wall. You're going to hit the wall. But if you have a double slit in classical mechanics, it's basically the same thing, where it's going to land in those two spots on the other side of the slits, and then your probability wave is going to be like this. But when you get to a quantum scale, it doesn't happen like that. It happens a little different. And so what it actually looks like is when it's firing, it looks like a wave coming out. And these waves coming on the other side of the slits are interfering with each other. And so you get this interference pattern that looks something like this on this probability graph distribution. And so we can try to find ways to interpret this, but pilot wave theory says that have basically your particle, which is propagating out a wave. The wave goes through these two slits that interfere with each other, and it's creating basically a path. And so if there's a wave, the particle is bouncing on its own wave front and propagating itself forward, and so it'll have all these different paths that it's going through, these potential paths that we can basically kind of determine where it's going to land. And so doing this, same with the Copenhagen interpretation, you can get the exact same pattern that what's actually happening on a quantum scale. It's just a different way of thinking about it. So in the Copenhagen interpretation, it says that it's always going to be a wave. That particle's not there. And then when you actually measure it, all of a sudden it's a particle. And then we're saying it's always a particle. It's just it's guided by its own wave. And then so, I think on the next slide, we show different paths they can basically travel along from the wave it's propagating out. And one more thing I was going to go over. But it has those the potential paths it can go down. And so for Copenhagen, actually go back one slide. Here. So when it's measured, that's where I was. So when it's measured, in the Copenhagen interpretation, we say that it's back to a particle. And when you're constantly viewing it, if you have a device that's measuring it, it reverts back to classical mechanics, and it'll just go have the original probability right here. And so we have to find a way to kind of interpret that into a way we can comprehend it, because if that is the case, we're saying that the second it's basically viewed or measured, that in the Copenhagen interpretation, the wave collapses. We can see right here that according to pilot wave, when it's being measured, it kind of warps these paths. So the particle going along, it'll be warped and it'll be more straight. So as it's being, you're basically just sending it straight forward as if it has a classical mechanics sort of path, or the way it's moving. And then so here is this wave distribution right here. And then right here is how the waves are interfering with each other and showing this probability. And then here is where, as a classical sort of, this would be when it's being viewed, and or just on a larger macro scale.
Okay, so where I come in. Okay. So before we dive into trying to understand what it looks like in the quantum realm, we first need to understand how measurements work in the quantum realm. Unlike in the physical realm, where when you shoot a tennis ball at a wall, right? Why we can see and observe tennis balls, because light is bouncing off of the tennis ball, right? But in the quantum scale, when you're trying to shoot an electron or a photon at a detector, try to detect it midway with, let's say, another particle, another photon, or another magnetic field, or another electron. It's like attempting to throw a tennis ball at a tennis ball to see where it is. That is very difficult. That is why we think that the measurement problem, which is when the Copenhagen collapse happens, isn't really enough to explain anything. It's very hand-wavy, it's very vague. It says it collapses, but what happens in that collapse? But before we get into that, we need to go through two ways to view experiments. There's one called thought experiments, using our imagination. Another one is using quantum hydrodynamic analogs, or analog experiments, using analogies. And two famous examples, one is when we are trying to study black holes. Obviously, we can't find a black hole on Earth, we'll be dead. But this case, we use something called sonic black hole. Instead of studying photons at the event horizon, we use phonons, also known as the quasi-particle of sound. Because at the whirlpool, we have an event horizon for sound where the water flow is faster than sound itself, at least sound in water. So we can study Hawking radiation, whether or not phonons actually come out directly correlating its circumference, the short shell radius, to the amount of phonons that come out. But that's a topic for another day. It deserves its own presentation. But today we're going to focus on bouncing droplets, which is often used as an analog to the quantum realm. So the all droplets involve silicon oil or any oil that has high cohesive strength and surface tension. And we'll put it on a dish on top of a vibrating speaker to simulate the non-zero background energy of the quantum scale, which also coincidentally is very useful for the bouncing for the droplets. And as long as the droplet does not reach below 100 nanometers of distance between the surface of the oil, it doesn't coalesce and merge back. That's why usually water just immediately merges back when you drip it, right? But this can prevent it from happening. So enter walkers and bouncers. No, not these walkers and bouncers, but talk about these walkers and bouncers. These ones. And as you can see, every time this droplet as a solid particle is propagating through, it's riding its own wave. It creates a standing wave that does not carry information, but it itself can interact with. And these standing waves determine the trajectory of the particle. Even though it's a solid droplet, a solid bead, but it behaves like a wave because of the wave that it produces. Imagine it like a surfer on a wave when they're going surfing. So, next. Yes, this is your turn.
So, bringing this macro experiment back to the single and double slit experiment I was talking about, basically, this doing it on macro scale means nothing unless we can first relate this to the quantum scale and say, this macro scale information experiment is actually accurate, so that we can draw connections between the two. But first, going into this, when we have these droplets on macro scale, go through something similar to the double and single slit experiment, what we see is something really similar. We see it propagating its own wave out, and we see it riding on the wavefront, and it has different paths because it's being basically influenced by the way its propagating wave goes throughout the surface of like the whole container. And so from like a side view, these look like walls. They're not actually walls, so what's happening is on the side view, it's just a slightly shallower area of the water. And the way the waves is propagating out and being influenced by a slightly shallower area. So it can actually go over this. But because of the way that this wave is propagating out and the way it's influencing with the shallower area, it's guiding it, kind of changing its trajectory towards this open area. And so from this, we actually get the exact same probabilities. So if we have the single slit, we get the exact same probability as we would on a quantum scale. Same with the double slit, we get this sort of interference pattern. Same thing with tunneling. So we can look at it, we can put basically a boundary of shallow, like a shallower area around the entire particle, and it eventually will go through. But the larger we make this shallower area, the as an exponentially harder time of basically going across it. So it'll be more contained. But you can see that it's been kind of being redirected, and so its trajectory is changing as it gets influenced more closer to the wall. I think that's all I want to say for this list. Yeah. So going further, that's just two coincidences. Here's our corrals. So if you do it in a circular, sort of like wall, like this is an actual wall, what we can see is its movement, because it's not being coalesced with the surface. It's actually just continuing to bounce around and move around. And we can use a tracker to basically track its movement. And over time, we can get probability rings that look super similar to that of an electron in an atom.
So just to point out a common misunderstanding, these dots around this ring is not included. We're talking about the central distribution because these dots are all iron atoms used to create a corral. So we're looking at here, the inside, to compare with this. Because these are equivalent to the barrier on the outside. Just imagine that.
So just like we have the probability rings in an atom, that we say electron has a high probability of being here, but it's not always going to be here, just like the path of this droplet right here. And so we can take this and even further do experiments to try to relate quantum scale to macro scale. And so this information was taken from experiments done at MIT. They actually have a lot of papers, and they replicated this over and over again to make sure it was accurate. And because of this, we can go further, because we can now relate quantum scale to macro scale, and we can take a macro scale experiment and get information out of it, and be able to relate it back to our theory. So because of these experiments, and because we have not only these quantum hydrodynamic analogs, we also have the tunneling effect also happening, and we all have the double slit and the single slit experiment having the exact same probability, so we can actually take information from this going further.
So next will be my turn. But before I go on to the next slide, the reason why I said that there's orbitals as confinement is because a common question children would ask as well is, why does the electron orbit, right, the nucleus? But if it actually orbits, we all know that if there's a magnetic field or electric field and a charged particle's going through it, it will start going through a circular path, right? And this will create and release synchrotron radiation, which we don't observe that in an atom. So are they actually orbiting? But if we model it this way, instead of a positive charge attracting a negative charge to orbit it, instead the positive charge is a confinement, a potential well. It models the electron as confined in a specific region instead of actually orbiting. Hence why you can explain why there is no synchrotron radiation actually being released, which is a common question. Next. So there is a phenomenon back in 1991, they identified as path identity, which is explicitly written in 2017. Basically, if a photon, if you shoot it through a beam splitter, and they end up in the same exact path, even if you shoot it one at a time, those two photons will get correlated. In Copenhagen interpretation, they can't explain this entanglement. But if you follow pilot wave theory, you can actually explain it. Because imagine the water droplet bouncing, right? It creates its own wave, but it also leaves behind a wake of waves going backwards. So if you send another particle in the same exact direction, they are going to interact with the waves that's been left behind by the other particle, creating a correlated outcome that Copenhagen would otherwise unable to explain. Next, please. So one interesting question is, can you measure a particle or detect particles without interacting with them? Well, they said we can. And there's a thought experiment called the Elitzer-Weidmann bomb tester, which has been experimentally carried out just without an actual bomb, right? So they found out that if you have a single photon sensitive sensor, to a point where if a photon actually hits it, it'll detect, right? You have a 25% chance to tell if the detector is there or not, or the bomb is there or not. Because Copenhagen would say that the particle went through all paths at once and then appeared at a detector, right? But if that were actually true, the bomb would have went off. But if you follow pilot wave theory, it can help explain the probability outcome because the photon only goes through one path, but the pilot waves explore all paths. Remember, pilot waves don't explicitly carry information on the macroscopic scale, only on the quantum scale. So it can interfere with its own pilot wave without actually hitting the bomb or the detector. And otherwise, in classical mechanics or a normal Copenhagen interpretation, the chances of detecting the bomb without interacting with it would be 0. So next. So this is what we believe pilot wave theory could solve, the measurement problem. Max Born had to create the Born rule to explicitly postulate and fix the measurement problem in quantum mechanics, which is why we have the Hilbert spaces and whatnot. It has to emerge out of the Schrodinger equation. But in the pilot wave problem, there is no need for that. The Born rule emerges from pilot wave theory. Entanglement, as we already explained, and all the rest, we already explained how it's actually explained by the pilot wave, right? But even crazier is, which is a paper me and Levi are writing right now, is how we think pilot wave could explain gravity. Very bold claim. So let's move to the next one. So this is just what we observe. Once again, credit to Levi for learning how to derive this. And basically, we wrote down Einstein's equations here. I know you can't really see it, but basically we were just comparing. We're like, wait a minute. So on the Einstein's equations, if you guys can't see, don't worry, I'll write it out for you. G mu v plus v equals to So this is what we call the stress energy tensor term, the matter term, and this is what we call the space-time term, which is space-time itself. And what it tells us is matter tells space-time how to bend, space-time tells matter how to move, explaining orbits and orbital mechanics and whatnot. But we also notice something in pilot wave theory. If you look at the polar form, there's a time derivative and spatial derivative, and we've realized that one part says that the matter tells the pilot waves how to propagate. The pilot waves tell the matter where to go. That sounds very oddly familiar intuitively. So, next part please. Then we realize something else. When you do a double slit experiment, So double slit experiment, right? If you have two slits, it acts as two independent wave sources. This is wave mechanics, right? So if we have two particles in pilot wave theory, each particle are their own wave sources. Now, we would obviously expect the probability distribution like this. But what if we add three slits? Or three wave sources, or three particles, or four slits? We realize that the probability amplitude to meet in the middle actually gets higher and higher. Gravity does that too. The more particles you have in a system, the more likely they're going to meet in the middle. Sounds like gravity. Next slide, please. So why does it matter? Why do we think pilot wave is such a big deal? It's because some interpretationists will say, shut up and calculate, right? Copenhagen would say that. They say that the wave function isn't real, the measurement collapses it, all you need to care about is the outcome, right? Don't ask how, why, or when. And other interpretationists requires tremendous implications, like 11 dimensions or infinitely many worlds, just to solve the same problem, or some of the problems. Next, please. So Copenhagen interpretation sort of shoves the problem of the observation and the particle-wave duality in a box. And there's so many questions and skepticisms for pilot wave. But remember, Richard Feynman himself, the pioneer in quantum field theory, he says that I would rather have questions that can't be answered than answers that can't be questioned. So why can't we question Copenhagen? And remember, George E.P. Boggs, his statistician, he says that all models are wrong, but some models are useful. So why not pick a more useful interpretation, more intuitive, something that can help us peek into the hood of how quantum mechanics work? And these are the common criticisms, by the way, for pilot wave theory. No unique predictions yet. Copenhagen can do that. Violates relativity because of non-locality of the waves. Hidden variables, the unobservable part of the quantum mechanics. Configuration space, where the wave is waving into, because we've been showing 2D diagrams, right? In real life, the waves should be 3D. So what is the wave waving into? Fifth and sixth is just saying that, okay, there's other widely accepted models, why should we care, right? It's just an interpretations, bro. Like, why do we need to care? So first, to tackle the first three problems is quantum fluctuations real? Real or BS? BS as in bad science, not bullshit, okay? We're professors. So, I got you there. Next is, well, no. Quantum fluctuations are very real. They have real consequences, such as the Casimir effect, which is if you have two thin neutral plates in a very small distance apart, they actually get close by unknown force or pressure. People say, oh, what if it's intermolecular forces? Well, it's too far away for intermolecular forces, but short enough so that the wave modes on the inside cancel each other out. Only few stable wave modes can exist by quantum fluctuations. So outside has more pressure than inside, closing the gaps. And then we have another one, a Aharonov-Bohm effect. Bohm did this research as well. Basically, if you have a solenoid and you have a magnetic field coming out of the solenoid, in classical physics, the external magnetic field is negligible. You can't detect it on the classical scale. But when you shoot photons or electrons at it, we see a phase shift at the back of the detector. That proves that even in classical physics, potentials isn't just a mathematical term in equations, they have real consequences. And then finally, it's hyperfine scattering. If you're a chemistry student or astrophysicist, you will know that at all spectral levels, you can zoom in to even smaller structures. That's what's called hyperfine structure. And it couldn't be explained otherwise, because if two electrons are on the same energy shell, they shouldn't have more smaller energies. But if you look at the hyperfine scattering effect, they can actually explain it, because virtual particles, whenever they appear or disappear, require slightly more energy or slightly less energy to excite them. So next, configuration space. So what's the wave waving into, right? It's just a wave, bro. But where is it waving into? It's 3D. Well, Einstein can answer that. Whenever Einstein talked about general relativity, space-time bends, as he would say, or gravitational waves, which is literally waving, but where is it waving into? No one asked him that, did they? This is the same grace we're asking from all of y'all when you look at pilot wave. We're asking for the same grace to have an assumption that waves, 3D waves are possible, but in this case it's a tensor wave. So if Einstein can have the grace to assume that there's a higher dimensional configuration space for gravitational waves and space-time geodesics, we're asking for the same for the pilot waves. Next is lack of experimental motivation. There's so many other widely accepted models. It's just an interpretation, bro. Why care? Why should we care about pilot waves? But that's why we're here. As scientists, engineers, and philosophers, and people, we're here to try and explain the world in a more intuitive and understandable way. We don't want to scare people off from quantum mechanics just because we do not understand it by saying, shut up and calculate. We want them to understand it better, peek under the hood. So why not use pilot waves, right? As Isaac Newton once said, if I ever see further, it's because I stand on the shoulders of giants. It's a letter to Robert Hooke, explaining his gratitude of all the scientists that came before him, establishing the foundations of what he can build upon. We should do the same. If we do not work on this kind of problems, if we just shove away pilot wave theory, it's an intellectual insult to their efforts and their discoveries. And then Carl Sagan also puts it in a perfect way. Science is a way of thinking much more than it is a body of knowledge. If we stick to our old knowledge all the time, we would still think that the Earth is flat or the sun moves around the Earth. But that's not it. Science is a way of thinking and investigating the world. So why not take an interpretation that helps us investigate it better? And finally, of course, Einstein. He says imagination is more important than knowledge, for knowledge is limited, whereas imagination embraces the entire world, stimulating progress and giving birth to evolution. Because all these discoveries are discovered through thought experiments. So that's our takeaway. So the takeaway is, give pilot wave theory a try. Science should never shy away from problems and questions, and ask more questions. Ask them boldly. Don't be scared. Don't be intimidated by the black box. Where's the black box? Is it gone? Click on it. Try. Oh, it's gone. There's supposed to be a black box here, but it's okay. So don't be intimidated by a black box. Just imagine a black box there. Whenever you give pilot wave theory a try, look at other theories as well. Look at the quantum Bayesianism interpretation. Look at many worlds interpretation. Try all of them. But each time you give them a try, ask, are they practical? What's the explanatory power that they carry? What is the predictive power they carry? Are they intuitive? Do they sacrifice determinism and causality for something else? For example, Copenhagen sacrifices causality and determinism for the mystical probability feature of quantum mechanics. But nothing happens for no reason. So don't be intimidated by it. And the box is here. So a theory should be just as intuitive and concrete as it is abstract, because math is a language. Languages are abstract. We use abstract language to describe a world that is concrete, real. So thank you for listening. This is all our sources. Feel free to talk to us if you really want all the sources of our research. And we also want to bring up, in 2 weeks, there'll be a mystery, another new presentation. We don't know who that is. It could be this very person in the same room. It could be someone in faculty. We don't know. But be excited, because every 2 weeks, there'll be exciting topics from professors and more students alike. So thank you very much for listening. Feel free to ask any questions. Like I said, ask questions boldly. Don't be afraid.
First of all, I just want to say thank you to you guys. You guys knocked us out of the park. I've been excited about this ever since you guys thought, we're coming up with this idea, and I know, Albert, you've been thinking about this for a long time.
Since I was 14.
I just want to say thank you to everybody who showed up. I think that this is just a beautiful moment for physics society. But so my question is to you, I'll give you a softball question first.
Sure.
So how do you think this could sort of, I guess, help the field of quantum computing?
Quantum computing specifically?
Mm-hmm.
So like I said just now, if we understand entanglement and other quantum behaviors much intuitively and better, we can design quantum experiments much better too. For example, just now as we have the slide for the path identity, Copenhagen couldn't explain that. Or the Weidmann bomb tester, it couldn't explain that. Do you mind going to the slide with the Weidmann bomb tester? That one? So there's another concept that's associated with this interaction-free measurement. We call it counterfactual computation. Computing without computing. That sounds dumb. But it's the same effect. If you shoot only one photon and it hits the right detector, it went through the entire circuit without actually going through it. And they found that this actually runs Shor's algorithm. Sorry, not Shor's algorithm, sorry. Grover's algorithm is a search algorithm for search trees way faster than any other algorithm. And you can tweak the probability depending on the refractive index of the material to up to like 88% accuracy. That's what I remember. And you can actually find that paper out there. They actually used Grover's algorithm using this concept, interaction-free measurement. So if more people understand intuitively how it works, they can design their experiments better. So that's a very good question. Does anyone have any other questions? Yes. Yes, here. It was beginning of the slideshow, so I think you missed that part because it came in later. Yes.
Presented by Levi in 1927. So that was when it was first thought of. It wasn't actually fully derived and like used yet until 1952. And so there's a little bit of a gap where until David Bohm picked it up, it wasn't really fully established yet. It was just thought up. And so yeah, so I guess kind of recently.
Also, why is it a big deal is that Louis de Broglie, the gentleman on the right, he is the one that postulated the matter wave idea, which is electrons can have the wave behavior too, and it was later proven. So I would think that he has the intuition of tidal wave theory correct. Otherwise, he would not have that postulate down to the T. So, good question. Any other questions?
So you were showing an experiment for the black hole and
Sonic black holes, yes.
Yeah, and how you could sort of see from this. You're saying that this experiment sort of proves the pilot wave theory?
Oh no. We're talking. This is just to introduce analog experiments.
Okay.
This is an example of analog experiments, but the one we focus on is this one.
Okay.
This is the one that helps us understand and study pilot wave theory better.
So do you know of any observations that have been made at actual black holes that maybe prove this?
That's the issue. No one has ever observed a real black hole until like recently, right? Using like a lot of like global arrays of radio telescopes to see the M87 picture of the black hole. But no one is close enough to probe it. No one is close enough, or no device is close enough to detect anything experimental related. However, we do observe superradiance, which is when a rotating black hole, the side where it's rotating towards you is actually brighter than the side that's rotating away from you due to the Doppler effect, this relativistic effect. And they found the same thing in an analog black hole, and dumb holes or sonic holes. Basically, they found that phonons, or the sound particles, the quasi-particle of sound, on the side that it's coming at you, the phonons are actually more intense, brighter than the side that's going away from you. So that helped them correlate the behavior of black holes. And using that, they tried to do experiments for Hawking radiation and other frame dragging and stuff. And they were quite reasonably successful in my opinion. So good question.
So yeah, sorry, I've got a ton of questions here. So quantum field theory is sort of famous for allowing particles to be, for creation and annihilation of particles, right? So how can you define definite trajectories when particles can simply just vanish or appear?
That's a very, very good question. Let me just show you something real quick. So, unlike Copenhagen, like I said, do you know the Feynman diagrams, which we usually use for explaining like how particles are created, like photons? Photons create into an electron and a positron. Have you positron? Have you seen this diagram before? Feynman diagrams. So Feynman diagrams, if you look at this, they're technically deterministic. Meet at one point, scatters at other points. You see? But Copenhagen says they're a wave until they're observed, the measurement problem, right? Isn't that more vague than the pilot wave theory? How does the wave interact and when, at what point those waves interact before they collapse and annihilate? Copenhagen isn't able to explain that. Pilot wave theory does though, because the particle's always there. So when they're close enough, they can annihilate because eventually they make contact. That's why I think pilot wave theory is more convincing, because it's more deterministic, fitting the picture of even Richard Feynman itself. So, but also another thing is it maintains causality. They don't explain how the collapse actually happens. So that's why I feel like it's a very big sacrifice. It's sacrificing causality and determinism for probability. I don't think that's a worthy sacrifice in quantum physics. So thank you for the question.
Yeah, that's like a whole different topic right here. It is matter and antimatter. So you're basically saying with enough light energy, you can split off into matter and antimatter. Whole different topic, but basically, I think what I'm trying to get at is you can kind of determine one equals the other two. These two meet, they annihilate, and energies are created. They're not. I guess you don't technically create or destroy anything. You just turn it to really.
So any more questions?
I'm not sure if you can touch on you guys talk about some practical application of what this.
So that's a very good question. So what me and Levi actually planning to do is, you remember this slide? Yes, this slide. Remember how we said that we're trying to write, we're already on the process of writing a paper on quantum gravity, how we can emerge from quantum mechanics, right? So what we're trying to do is we're going to use the analog experiments, the same analog droplet experiment, to put as, so let's say we test with 2. How does the path go? And we test with 3. How does the path go? We're trying to see if the amplitudes in the center actually increases as the theory goes. And with that, we can have a better understanding if gravity can actually emerge, because otherwise because we don't have the apparatus to test quantum experiments yet in UCO, so it's kind of hard.
We had the analogs done already for us through the MIT.
Yes, MIT study.
research.
Just want to first replicate.
It's never been related to gravity, so basically that's where we're taking it. So we can take something that's already been proven and it's already been published, and then we can try to relate it to something new. Because with this, try to allow it to explain gravity is entirely different. So it hasn't really been touched up on by anyone, and we've kind of searched around and no paper has mentioned like, hey, this like way of interpreting what's happening on a quantum scale can actually show us like what gravity really is.
And another thing is, like I said, it could help explain a lot of things that can happen on the quantum scale, helping us improve like for things like quantum computing. But you also have to realize, because Bohmian mechanics have been shoved in the dust for so long, not many people have enough time to put thought into it to come up with practical experiments. These are the closest thing we have. So right now what we're planning to do is first we replicate the experiments at MIT, then we'll start getting into like more novel ways, novel approaches. So yeah, thank you.
Which this is kind of connecting ideas to draw a conclusion to say, hey, this can explain gravity, but we were a little hand-wavy with explaining the Schrodinger equation fully written out to Einstein's equations. That was a little hand-wavy, as Professor Prather would say, but this is more of, hey, we're taking ideas that have already been proven, that have already been written about. There's actually like, you can see like a connection between them. No one's ever thought about this before. Let's go ahead and draw that connection.
And we are also, so while we're working on this hypothesis paper, we are also working on a separate theoretical model paper, and in attempts to try and derive, at least attempt to derive hydrodynamic equations and relativity from Schrodinger equation and the pilot wave equation. Because what we notice is, in general relativity, they use tensors. And tensors and matrices can be expressed as systems of differential equations, especially partial differential equations. Fluid dynamics, as well as the Schrodinger equation, especially if you divide it into x and y and z axis, is a systems of differential equations. If we are somehow able to map that into matrices, we think we could possibly derive general relativity from quantum mechanics?
I think that the reason traditional interpretation and use of quantum mechanics won out amongst the various other theories was because it was easier to compute things especially by hand. We didn't have computers then. And now it may be possible nowadays with better computing power to go to these other theories and take
what we
take
talked
a
about
realistic
earlier.
second look at all of it. But one of the big complaints about pilot wave, I think, was the difficulty of having multiple particle.
The many-body problem.
Yeah, many-body problem.
I think even in classical physics, right, many-body problems is a problem.
Well, it is, but and it was a long struggle. But ultimately, I think still, at least right now, the traditional quantum mechanics approach on the multiple particles is we know how to handle it. We know how to make predictions again with computers.
Mm-hmm.
But in the early days, they didn't have that, so that's the reason.
Exactly.
Yeah.
That's why we
And
say
you really
we should
can't
bring
you
it
really
back.
can't blame them for doing that because that was the whole.
It's true. Yeah, there's limited computational power back in
Yeah,
the day.
that's right.
That's good. So now, since we do have access to more computational powers, especially of many GPUs, right? We hope that in some day we could simulate these things more accurately, especially with pilot wave theory. That's why we hope to bring it back. It's been in the dust for so long. Now many worlds interpretations coming back to the spotlight. But I was like, wait, but what about pilot wave? Why hasn't anyone talked about it yet? So that is one of the reasons we bring it back up, is so that people explore more different interpretations and in hopes to create better models in the future.
I think our thought process is if we can explain quantum mechanics in a more intuitive and deterministic way, and we get what it's mainly used for advanced further, then our ability to basically compute things also increases. So trying to be able to accurately describe what's actually happening could actually help us out down the road. It's just the right now computing is like the main issue. But in my opinion, like despite whether it's more complicated, I think it's better you go for the more accurate one. But then that's the thing: is this accurate or is Copenhagen accurate? And then so we can try to run experiments and try to figure out. So like if we run an experiment and we like this isn't working, I think Copenhagen actually had it right. Well, then we get data either way in our experiment. We get data proving against or for pilot wave theory. That's why I'm like, we should like figure out a way to kind of know what's actually happening.
So, there's a lot of like talk around this theory about how it's not able, you can't derive relativity from it, right? And so, I mean, and I understand you say, okay, well maybe this can explain gravity, right? So we're not throwing out relativity with this, right?
No. So pilot wave theory on its own, the one that's explained by Louis de Broglie, is the one that has trouble accommodating special relativity. However, the Broglie-Bohm extension done by David Bohm actually includes relativistic equations. And you have to realize, even traditional quantum mechanics, they can't merge with general relativity. Even special relativity on its own cannot merge with general relativity because special relativity has mostly been applied in quantum field theory, and even that cannot merge with general relativity. So I think it's more of a intellectual gap. But however, if you think about it this way, if we truly proved and shown that we can derive gravity from quantum mechanics, we just married general relativity and quantum mechanics. We solved quantum gravity. So that bridge, that gap, the chasm of ignorance, as people would say, is naturally emerged from pilot wave theory. That's what we're trying to solve. But if it fails, it fails. Just like any experiment, right?
We're not saying that's easy though. We're saying
Yes.
there's a possibility.
Yes.
It's probably very, very difficult, but there's a possibility over the interpretation we're looking for.
Yeah.
But like I said towards the end, right? Don't be afraid to ask.
Yeah,
right?
no, I think what this shows is it really shows the power of curiosity, right? You guys are very curious about this. And I thought it was hilarious how Levi was just like, well, you'll learn this in quantum mechanics. And it's just like, well, you don't learn quantum mechanics until you're, maybe in your graduate
Last
degree.
semester, so for EP, it's recommended you do it last semester.
Yeah.
And then most semesters they don't actually host it because you need 4 students enrolled.
Yeah.
And so if you don't have 4 students in
Yeah.
any EP major wanting
Well-
to take quantum mechanics, then you can't host it that semester. You gotta wait a semester and extend it. So
Yeah. Well, what I'm trying to say, and everybody here, like, if there's something you're really curious about, even if, you know, maybe it's something you didn't learn exactly from school, or maybe it's something you did, we would be more than happy to have you guys give a talk on that. I mean, of course it needs to be physics related, but what isn't physics related, right? So yeah, we just want to open the door to not only faculty, and professors, and but also students. So
I guess.
if you're driven and as curious as these two, we would love to have you guys give a talk on something you're just as curious about.
So any other questions? Let's talk to Taylor.
So can you, if you start from the Schrödinger equations, how do you, so what is the starting point, like, in terms of deriving the tidal wave? Does it emerge out of the Schrödinger equation? Is there a way to do it?
Yeah.
yes,
So I mean,
this is starting from the equation, and we're basically just expanding it out. So this is the full equation right here. All we're doing is just taking our wave function right here, putting it in polar forms, and we're taking our Hamiltonian and writing it out. And then once we do all of that, this is our long extended equation. It's not exactly pretty, but some of this, as you can see, have imaginary parts to it. And basically all was done was just split the imaginary part from the real part. Obviously, between here and here, or between here and here, and here and here, there's a lot of steps that I couldn't fit on this whiteboard, and I probably couldn't even comprehend it yet, because I know what these symbols mean. Like, I can say the gradient squared as Laplacian, like there's the Planck's constant, right? But I'm a sophomore.
so we still need some time before we can get there.
For sure.
So in that equation down there where you have V is equals to
This one?
Yes.
So this is the guiding equation. This is the velocity of the trajectory of the guiding waves pushing the particle. So this will be the velocity of the particle. This is the guiding wave itself, the phase of the particle, the wave, and this will be the mass of the particle.
So what's your immediate next step?
So like
Write a hypothesis paper. So basically take everything we have in this presentation, everything we know about it, and basically just write a paper saying, like, not going into all the math yet, but trying to basically say, like, hey, this is our idea, this is what we think could come out of pilot wave theory, get that published and out there, and then our next steps would be, now we have to actually prove it through like not only computation but also experiments. So there's the 2 sides of it. We could run our analog, so our hydrodynamic, basically oil bath. We can get that set up, and we can get a tracker, and we can basically go further beyond what was done at MIT.
unless UCU has the budget to make quantum experiments.
Let's go.
Yeah, that'd be our next step. So our first step is 3 types of papers. Start with the hypothesis. Then we'd what's the theoretical called? What's the name for it?
So hypothesis paper, then theoretical model.
Theoretical
Right.
model. And then we'd go into actual experimentation.
Experimental paper. So this is the 3 steps we're going for. But the first step is writing the first hypothesis paper. Next we will be working on the math and the formal language of it, formalizing into abstract language, and then we do the experiments. That's the step 3.
As of
Phase
now-
3, not step 3 then. It's not that simple.
As of now, we're starting the hypothesis paper. We have this presentation, and we have a whole abstract. So we're kind of in the very early stages.
I
We
would
just wanted to
really-
get our idea out there.
I would really love to see where the math goes, because quantum mechanics is famous for the renormalization theory, and which sort of helps get rid of some of the infinities that occur. And so, from what I've read, is putting pilot wave theory on top of this, you get more. There's possible that you're going to get more infinities. So. I don't know if you guys are thinking about this, but I don't know. I'm just curious to see where the math goes. And so, have you thought about maybe who you're going to reach out to help you with the math? I mean, this is some.
Not yet. But-
Anyone wants to volunteer?
Yeah.
Yes.
yeah,
Any
yeah.
professor here interested?
Reach out. We also reach out to the math department.
Mhm.
I know McClendon almost, I'm not sure where it's gone, but he thinks he solved the twin pipes conjecture, which is huge. So
Yes, one of the big
we
conjectures.
can ask for some math power behind it.
Yes. Like also, the exciting implications of deriving the math for this is we are instantly uniting four different branches: fluid dynamics, statistical physics, quantum mechanics, and relativity. Because if we're able to derive this equation, because it has fluid and wave mechanics in it, and derive it into general relativity tensors, right? Using the Schrodinger equation, we just united four branches of physics. The always hope for grand unified theory. However, we do need to point out a caveat here is, like what Carl Sagan says, extraordinary claims require extraordinary evidence, and the evidence part is what we're trying to work on. So, yeah, give us some credit. Take our models with a grain of salt. Yes.
So your major is computer science?
Computer engineering. I minor in mathematics, but I'm also interested in other fields.
Do you see the possibility this learning of this system from to some point of your profession
Yes.
or just out of interest? How you are into?
I think they're all related. But I think the problem with me, a lot of people complain about this, since I was young, is that I don't see different branches of science. To me, biology is just as intuitive as physics, because you can derive chemistry from physics, and then chemistry can derive into biology. It's just more complicated. That's it. At each time step. And just like John von Neumann, he's the one that gave us the von Neumann architecture of our modern day computers, right? All the chips and CPUs and whatnot. Those architectures inspired by him. He is also a statistician. He's also a physicist. He is also the one that created the idea of, I think Shannon entropy. No, Shannon is called Shannon, but another version of entropy, I forgot. But he worked in so many fields because they're all related. At the end of the day, all fields of physics are related. And whenever you have a project in any field of science, especially on a large-scale problem, you cannot only have one field. You need all of them to have a proper picture of how to solve the problem. That's how I feel about physics. That's why I'm so excited about it.
But the correct interpretation of you, if it helps us to further where we are in quantum computing, like it's had actually big about.
Yeah, true. And also one more thing is when they first discovered spectral emissions and in atoms, right? They did not expect the future to use it for lasers, which they did not expect in the future to use for grocery barcode reading, right? Or laser photonics and even eye surgery. Back in the day when people discovered this phenomenon, they did not say 10 years from now they're going to use this for grocery shopping. No, they didn't say that. They just discovered it because of the idea, the knowledge behind reality. But as engineers, use that knowledge to create something else more useful. And that's what we hope our model can do down the line.
Yeah, I think it's promising for quantum computing because the Copenhagen interpretation talks about the collapse of this wave, right? Where if this collapse really happens, well, then from what I've read is like then that's sort of we have to throw out quantum computing there, and so if pilot wave theory, if you guys can help it survive, right, then it sort of gives more promise to quantum computing.
Sure. So, that's what we're
This is kind of like it's a way of viewing it mathematically. Both are going to be probably about the same. That's why it's a counter argument because you can't prove it either way. The equations are gonna they're going to both be true because you collapse the wave function, it's going to act classically, and if you have on the slide where it's like warping it and it's also acting classically, it's going to have the same outcome. So there's no proving it either way. That's basically all we're trying to do is basically say like this is a more deterministic way and like it's a better way to comprehend it, to know what's actually happening instead of just saying, oh, it collapsed.
And also, think of it as a pilot project, no pun intended, but a pilot project for future development for quantum computing or whatnot. Because once you're able to comprehend it better, it also helps students because it's less intimidating, right? You can see what's going on, at least imagine what's going on. It becomes less intimidating, more people are going to go into it, and more development can happen in the future.
So remind me the name of the guy who came up with So that was in the 20s.
1926.
Okay, so and you said it was like kind of shelved for a while, like that idea.
So
Okay. So
Yeah,
it was-
Bohr sort of talked him out of it, I guess.
Okay, and then so in the from the 1950s till now, or maybe that experiment at MIT, how much has it really been studied? Like, did it not kind of like what does that timeline look like from? You said you got picked up back in the 50s until that.
and then it was derived, but for the most part, if we have the widely accepted Copenhagen interpretation, and its equations are getting us solutions that are accurate, then there wasn't really like I guess we had those.
There's no incentive.
There's no incentive to go further because they're like, oh, these equations are accurate. We can move on because all we need is those mathematical equations to get the correct answer. But every now and then you'll see like the all the experience at MIT where they stop and they're like, hey, maybe this interpretation is a little different. Let's run some experiments on it. And so it's not that like there just weren't. Basically, not as many scientists were focused and like they weren't incentivized to go through and just try to derive some new equations when they already had equations in front of them.
Yes, like I said towards the end of the presentation, there isn't enough incentive, right? If there's already a working model, so why do we need to go another alternative model, right? And also another thing is, ever since David Bohm re-derived it, it's been shelved again. That's why it's rarely inherit till modern day, like today. So it's unfortunate, but it's true. And also, it could also be because David Bohm has some association with the communism or whatnot back in the day. They shelved his stuff. You know, that could be. We don't know. But
Well, also like if we follow the interpretation of the sun's orbiting around the Earth, or, the sun's orbiting around us, well then it can make like sense in your head. You can just go on living, and you can just basically say like, well, my equations are true. There's no need to dive further. But then if you want to say, is that exactly accurate? Is that actually happening? So that's basically where pilot wave theory comes in. But we're not saying pilot wave theory is 100% accurate. We're saying that
it's promising.
It's promising.
So I can tell you guys are very passionate about it, and I always love to see people passionate about something. I feel like it's nowadays that's pretty rare in people just to see someone passionate about something. Is there anyone that like you said you've been interested in this since you were 14? Is there someone that introduced you to like maybe your parents, or how did you stumble upon this to where I can tell
Just asking questions.
there's such an interest? Where did that interest start? Like,
Asking questions. You can ask my parents. They think I'm the most annoying child. Every time I'm watching a movie, I'll ask why, and that gets so annoying. And the same thing. I asked my dad, how does a light bulb work? He just said electricity goes through, heats up wire. I'm like, but that's incandescent. And he's like, that's all I know. And then I'm like, okay. So I started looking into it. I was like, oh, it's got electrons. I started like noticing different mechanics in different devices. And I was like, okay, let's dive deeper. And once I reached quantum mechanics, they're like, Copenhagen, particles a wave, collapse. That's the end of story. I'm like, that doesn't explain shit. So that's why I started looking at different interpretations. Quantum Bayanism, many worlds interpretation, or even string theory. And I'm like, wow, all of these are fascinating, but what do you mean by 11 dimensions? What do you mean by infinitely many multiverses? And how can you prove that?
The question here, even though you have that deep interest on the physics, why you choose
Computer engineering. So that's a very, very good question. Reason is because I'm also interested in machine learning, and I believe that there's a lot of problems humans can't solve that machine learning can help. And since I like so many fields, the best way to touch on so many fields is computer engineering, because every field needs computers. So, and also because money. Yeah. So that's why.
I've got one question, because I know you guys made a good analogy with making a measurement and trying to fire another thing to measure it, right? So does this pilot wave theory not solve, but have if making a measurement affects the measurement itself, does this have that problem too? Like
Yes.
Okay.
It still happens because, like I said, we're still throwing tennis ball. However, I feel like the best hint we have is the interaction-free measurement. this one. Oh no. This one.
Yeah.
I feel like being able to phase shift something just by the design of the circuitry and the path of the photon gives us hints on how to measure something without measuring them. And that could negate the need of throwing a tennis ball at the tennis ball. Because you are just influencing the tennis ball itself. The path of the tennis ball itself is influenced. And Copenhagen would just say, you just went to all paths. But Pilot wave says the waves are the ones that's causing the effect. And I feel like that's a good hint on how to solve and overcome this measurement problem.
Cool.
Yeah.
Okay, could you explain this picture, what they are talking about?
Oh yes, I can explain it again. So this is known as the Elitzer-Weidman bomb tester. So before we get into this, the simple question is: can you detect anything without particles? Without interacting with the particles? We call it an interaction-free measurement. It's been proven. So without bombs, of course, but they proved it by using interferometry, using the Mach setup, and they found out that even if there's a detector, right? Let's assume there's a detector B, which is the bomb. And if the detector B is there in the way, can we detect detector B without touching detector B? The outcome is 25%. There's a 25% chance that when the particle goes through and it hits the right detector, there's a phase shift. So the wave function would shift. The probability distribution would shift. And that shift can tell you, oh, there is something there. And if you remove the detector from there, the shift would be different. So this is called an interaction-free measurement. That's a bunch of experiments similar to this. Like I said just now from Josh's question, counterfactual computation is computing an outcome without computing it. That makes no sense, right? But it's the same thing. They shoot photons through a circuitry, and they can run a switch algorithm called Grover's algorithm to switch through a solution space without shooting photons through. It's very weird.
So those computation principles, how closely are they related to current day, deep learning, and machine learning? How far they are?
So how far in do we have this something? Very little. Like that's what surprised me is because interaction-free measurement is so rarely studied. I feel like it's kind of sad because right now we're focusing all on the alternative, which is machine learning, AI, and whatnot. But there's a lot of potential to quantum computing, especially counterfactual computations, because it can make even more sensitive instruments, and it can even make it more efficient. Like for example, even general quantum computers can already do exponential speedups of computation that a lot of classical computers can't. So I feel like quantum computers are still 20 years, 30 years away from reaching our classical computer skill. Yeah. And I feel like that's just how technology is. If you are not exposed to it, not enough people talk about it or think about it, then not enough people experiment.
So current quantum computers are all designed to very low temperature.
Super low.
And if this experiment also need that very
No.
low or
No, it doesn't. Photonics, that's why I feel like photonic quantum computers is the most promising one, because they use room temperature. All you need is a vacuum setup. So they're in a vacuum, just shoot light through, and if you design a circuit well enough, of course that's not easy, but if you design a circuit well enough, you can make computations that otherwise is impossible in room temperature.
so for the current quantum computer, the basic building block is just
There's a bunch. So
superconductor junction.
yes. So
What will be the basic building block?
Photons.
Interferometer like this?
yes, photons. The photon itself.
Photon is the probe, right?
No, the photons is the qubit, but these are the gates. Imagine the lenses as the gates. As it passes through a specific refractor or a specific reflector, it phase shifts the, the photon's polarization, or depends how you want to measure it, but usually it's polarization. And that, especially after it's entangled with another particle, would interact with each other, right? That in itself is a computation. And here's the best part. It happens at the speed of light, because it's light. So the problem now is, because photons are they're bosons, they don't interact with other particles that well. it's also very hard to measure and interact with them. It's hard to make two photons entangle. It's very hard. No one found a very efficient way yet. But China claims they have, but I haven't seen any articles about that. But they claim that they have, and if we're able to counteract this entanglement problem, because boson's nature, right? We would have functioning photonic quantum computers in room temperature. It's very fascinating. Yes. So, any other questions?
So what kind of background do you need to, so you say you're working on some theory and things like that, so what math courses or what physics courses do you need to be able to come up with a theory and everything?
I feel like you just need to go through the problem first. Look at existing solutions to the previous problems, and I realize you need linear algebra, matrices, you need differential equations, something I'm failing this semester. But it's these aren't all necessary tools that I discovered along the way, which at first I did not have interest in differential equations. But now, after discovering problems like this, I'm like, oh, it's related, and now it piques my interest more. Because I realize that's the tool I need to solve a problem like this. So you can start from any background. You can be an art student, music student, any student, but you just need a curiosity, and then you can start anywhere.
Recommendation of classical mechanics, because if you're going further beyond, it's good to know what you're starting.
Yes, definitely. So, any other questions? No, I guess we can call it a day because now it's 4:06. So thank you guys for coming.
So we'll have another presentation again in 2 weeks' time from today.
Yeah. we have a mystery presenter already. So look forward to that. Look forward to that.
Yeah, and so probably next Thursday. No, we've got one. We've got one. And so we will probably announce it next Thursday.
Yes. We'll announce the presenter 1 week from now. So be excited of who this person is.
We already have this photo edited. We're basically just going to turn this into color, and you'll be able to see who it is.
Thank you so much.
Really good stuff.
If you guys have any more questions, feel free to come talk to us after and or later.
I saw the chairs in the room.
You mentioned quantum by right? Yeah. So I was reading into that last night, and reminding myself about all this. I think I told you guys last time we were here.
Yeah.
Quantum mechanics. I wrote a paper about why I didn't agree with the host.
Yeah, me too.
And I definitely
That is good, Dr. Teo.
There's more people every time, right? Yeah, and I don't know.
So who is that? Yes.
How you doing?
because you can put your hand around it. So what is it?
Exactly.
Prayer.
Shoving it.
Yeah.
Okay.
I got a picture of it.
I talked to you about it yesterday, and I said I was thinking to myself, I was like, after seeing that,
Yeah.
my idea is not worthy of being presented.
It doesn't matter.
I was like, mine is gonna be some little kiddie version.
Well, at this point, this is how I think about it. There is nothing like a dumb. It's about creating an environment where people can meet and talk, bounce off ideas. So there is nothing like a stupid presentation.
Yeah.
If anything that you want to contribute,
Yeah.
feel free.
It helps that, they knocked it out of the park the way they did, for sure. But and also it gives people a chance to talk in front of people. Because for me, I need that. I need to be able to talk in front of people because I have such anxiety when talking in front of people. So the more I do it, the better I get. Right? And I think we all need that, right? And
It's going to have a...
So 2 weeks, 2 weeks from today is the 24th,
So there's really no way to distinguish.
which I think that should be like the last.
Probably. Yeah.
There's no way of knowing. I mean, I could say that's what.
Yeah, because after that, it's only, 2 more weeks to school. Right? Yeah.
So certainly.
But also, so
The path, right?
there is not much homework for
Yeah,
to
so
go
classic
through.
Yeah.
mechanics.
Would you be able to present something?
Yeah, for sure.
And they can also submit
Any
something.
electrons of any spin.
Um, Is there going to be like so for the ASME symposium? There was like a deal to submit your abstract to. Is there going to be? Oh, there is.
Or this.
Okay. I guess I didn't.
I talked more with Ted,
That
Bert,
take a step
and
further.
I'm going to send out like a reminder.
Uh-huh.
But this is the website. It's okpvri.org.
Okay. Is that in the email that you sent?
Yes, it is.
Okay.
And if you click on the website,
Yeah,
it
yeah,
brings you
Slot
here.
machine.
Oh, okay. Maybe I didn't see that. Yeah.
And this is open to anyone.
Okay.
You just register. It's going to ask you, do you want to present something?
Okay.
So you can choose a poster presentation.
Gotcha. Okay. Cool.
So we really need, UCO to be like well represented. So we want to get as many presentations.
Well then, yeah, I'll register as soon as I can for sure. But yeah, no, I'm excited.
I hope that more students can take some classes in, for example, analytical mechanics helps with understanding like classical Hamiltonians and things like that.
Most definitely. I mean, like I said earlier, the math is really interesting to me because I'm like, how are you going to? Because I know that, for instance, in the easing model that I talked about, they use sort of transfer matrices, which I believe come from derivations through quantum mechanics. And so it's not the easiest way to derive something. I mean, it's of course what you need. But yeah, so that's what I try to harp on the note all the time is like, okay, how are we gonna do this?
I mean, I would like to think there's an objective
because I don't have. I mean, I'm decent with math, but whenever it comes to like higher level stuff, like transfer matrices and things like that.
Do you need help though?
Definitely gonna have to. But I think that's something that I plan to work on over the summer. Just getting better at that.
Which right now?
Let's go do that.
I mean, you're pretty proficient in some of that stuff, right?
Yes.
Yeah. So I have a solution. Potential
Well,
solution.
as I said, once we come to,
Yeah.
if there is something that we need,
I was sitting here just
there is always,
racking my brain and
get
getting
help.
there's gotta be
The
some.
problem is not help. I think the problem is
Maybe a
the
good
idea.
analogy, but if I'm trying to measure where the ball is, I throw a ball at it.
We're gonna go move that furnace real quick.
First? Oh, okay, cool.
Maybe move this
Okay.
first.
Yes, we got